Hello all, welcome to Broadcasting and Streaming Techniques session. This is Dr. Isakimuthu. We are discussing about transmitting digital television signals by satellite DVB-S S2. In that we are going to discuss, we have discussed about system parameters.
We are going to discuss about the DVB-S modulator now. Now, whatever I'm going to explain, I'm going to explain all component parts of the DVB-S modulator in detail. This particular portion, this circuit, is also found when we are going to discuss about DVB-T modulator. So, you have to be thorough with this DVB-S modulator, right? So, look at figure number 5. The first stage of the DVB-S modulator is the baseband interface. This is where the signal is synchronized with the MPEG-2 transport stream. This MPEG-2 TS consists of packets with a constant length of 188 bytes, consisting of 4 bytes header and 184 bytes payload. Payload means the real data are present. 4 bytes is for the header. The header beginning with a sync byte, SYNC byte. So we'll come to know where exactly the particular transport stream packets. This has a constant value of hexadecimal 47 and follows at a constant interval of 188 bytes. In the baseband interface, the signal is synchronized to this sync byte structure. Synchronization occurs within about 5 packets and all clock signals are derived from this. In the next block, the energy dispersal unit. Every 8th sync byte is first inverted, that is 047 then becomes 0B8, hexadecimal B8 by a bit inversion. The other 7 sync bytes between these remain unchanged. Using this sync byte inversion, additional timing stamps are then inserted into the data signal, which are certain long timestamp over 8 packets compared with the transport stream structure. These timestamps are needed for resetting processes in the energy dispersal block at the transmitting and the receiving side. This in turn means that both the modulator or transmitter and the demodulator or receiver receives this sequence of 8 packets of the sync byte inversion transparently in the transport stream and uses them to control certain processing steps. It may happen that relatively long sequences of zeros and ones occur purely accidentally in the data signal. However, these are unwanted since they do not contain any clock information or cause discrete spectral lines over a particular period. To eliminate them, virtually every digital transmission method applies an energy dispersal before the actual modulation. To achieve energy dispersal, a pseudo-random binary sequence, PRBS, look at figure number 8, pseudo-random binary sequence is first generated, which however is restarted time and again in a definite way. It's a pseudo-random. So it looks like a pseudo, but it is random, but it's not a random, it's a pseudo-random. In DVB-S, the starting and resetting takes place whenever a sync byte is inverted. The data stream is then mixed with the pseudo-random binary sequence, PRBS, by means of an exclusive OR function, XOR function, which breaks up long sequence of ones and zeros. If this energy dispersed data stream is mixed again with the same pseudo-random binary sequence at the receiving end, the dispersal is cancelled again. The receiving end therefore contains the identical circuit consisting of a 15-stage shift register with a feedback. which is loaded in a defined way with the start word whenever an inverted sync byte occurs. This means that the two shift registers at the transmitting end and the receiving end are operating completely synchronously and are synchronized by the sequence of 8 packets of sync byte inversion block. This synchronization only becomes possible because the sync byte and the inverted sync bytes are passed through completely transparently and are not mixed with the pseudo-random bit sequence. The next stage contains the outer coder. Look at figure number 5 and 9. The Reed-Solomon forward error correction. At this point, 16 bytes of error protection are added to the data packets, which are still 188 bytes long but are now energy dispersed. The packets now have a length of 188 plus 16, 204 bytes, which makes it possible to correct up to 8 errors at the receiving end. If there are more errors, the error protection fails and the packet is flagged as error by the demodulator and by the transport error indicator in the transport stream header being set to a 1. Frequently, however, burst errors occur during the transmission. If this results in more than 8 errors in a packet protected by Reed-Solomon coding, the block error protection will fail. The data are therefore interleaved, that is distributed over a certain period of time in a further operating step. Any burst errors present are then broken up in the de-interleaving at the receiving end. Look at figure number 10. And they are distributed over a number of transport stream packets. It is then easier to correct these burst errors, which have now become single errors and no additional data overhead is required. In DVB-S, look at figure number 11. In DVB-S, the interleaving is done in a so-called four-knee interleaver, which is composed of two rotating switches and a number of shift registers. This ensures that the data are scrambled and thus distributed as unsystematically as possible. The maximum interleaving is over 11 transport TS stream packets. The sync bytes and the inverted sync bytes are precisely follow a particular path always. This means that the speed of a rotation of the switches corresponds to an exact multiple of the packet length, and interleaver and de-interleaver are synchronous with the MPEG-2 TS. The next stage of the modulator is the convolutional coder, trellis coder. This stage represents the second so-called inner error protection. The convolutional coder has a relatively simple structure, but understanding it is not quite as simple. The convolutional coder consists of a 6-stage shift register and two signal path in which the input signal is mixed with the content of the shift register at certain tapping points. The input data stream is split into 3 data streams. The data first run into the shift register where they influence the upper and lower data stream of the convolutional coder by XOR operation lasting 6 clock cycles. This disperses the information of 1 bit over 6 bits. At a specific points, both in the upper data branch and in the lower data branch, there are XOR gates which mix the data stream with the content of the shift register. This provides 2 data streams at the output of the convolutional coder, each of which exhibits the same data rate as the input signal. In addition, the data stream was only provided with a particular memory extending over 6 clock cycles. The total output data rate is then twice as high as the input data rate, which corresponds to a code rate of 1 by 2. An overhead of 100% has now been added to the data signal. So that's all about the modulator, DVB-S modulator. We will see about conventional coding in the next session.